We've been looking at individual atoms and molecules, but substances exist in bulk quantities. This large collection of atoms and molecules comprise a substance's state of matter. This table compares the different criteria to distinguish one state of matter from another. Stop the video and review gases, liquids, and solids. Note that gases are compressible, which is why gases are involved with work, whereas liquids and solids are not. Also note that gas molecules are far apart, which means there's only weak London forces between gas molecules. As molecules move closer, the chemical forces get stronger, which is what we see in a liquid. Molecules are really close together in a solid. A liquid is held together by intermolecular forces. When the liquid is heated, those intermolecular forces break and the molecules move apart. This is what happens when a liquid evaporates. Note that the strong interatomic forces are not broken. In an earlier video, we looked at how structure determines shape, which determines polarity, which determines intermolecular forces. Stop the video and determine the intermolecular forces in these four substances. And the answers are: water has all three intermolecular forces, which is why it has the highest boiling point. CO2 is nonpolar with weak London forces, which is why it has the lowest boiling point. H2S, that rotten egg odor, is bent and polar like water, but no hydrogen bonds, so it's a gas at room temperature. Crude oil consists of organic compounds called hydrocarbons. These nonpolar hydrocarbons are held together by London forces. Note that as the size of the hydrocarbon increases, the boiling point increases. So the larger the molecule, the greater the London forces between those molecules. Let's talk about gases. Stop the video and answer these three questions. And the answers are: we can describe gases with the kinetic molecular theory. To answer question 1, gas molecules move very fast in constant random motion, and they're point size, which means that they're far apart compared to the size of a gas molecule. The chemical force between gas molecules is not strong. We assume there's none at all. How does temperature and pressure affect a gas? Stop the video and answer these two questions. And the answers are: these three assumptions are valid under ideal gas conditions, so stop the video and answer these two questions. And the answers are: at high temperature, we'll say 273 Kelvin or 0 degrees Celsius, assumption 1 is valid. Under low pressure conditions, we'll say less than 2 atmospheres pressure, assumption 2 is valid. What makes a gas ideal? Let's compare methane to steam to CO2. Stop the video and answer these questions. And the answers are: and here are the reasons. Look at the intermolecular forces. Water has strong intermolecular forces between water molecules. The steam vapor you've seen are water molecules sticking together. Methane and CO2 are nonpolar, so they have weak London forces between those molecules. We assume gases move very fast in constant random motion, but do methane, water, and CO2 move at the same speed at room temperature? Stop the video, look at these two equations, and answer that question. And the answer is: m is mass, so larger gas molecules move slower than small gas molecules. These three assumptions describe an ideal gas, but is it possible for an ideal gas to condense? Stop the video and think about that. And the answer is: if there are no attractive forces between gas molecules, the gas cannot condense to a liquid. If a gas is subjected to a high enough pressure, the gas will condense to a liquid. Stop the video and answer this question. And the answer is: as pressure increases, gas molecules move close together and are no longer considered point-sized. And as gas molecules move close together, they will start to attract and repel each other. A gas that's subjected to a low enough temperature will condense to a liquid. Stop the video and answer this question. And the answer is: as the temperature drops, gas molecules move slower. And as gas molecules move slower, they will start to attract and repel each other. For those of you who've been in a mosh pit, stop the video and explain how is a mosh pit like an ideal gas. And here is the answer. I'm more familiar with the gas part than the mosh pit part. Temperature, pressure, volume, and moles are needed to describe a gas. Stop the video and review these definitions. Note that changing one variable will affect another variable in a gas. Let's look at a few situations which involve gases. First, let's look at a marshmallow. A marshmallow has air bubbles trapped within a sugar matrix. The pressure inside an air bubble equals the atmospheric pressure. So stop the video and answer these two questions. And the answers are: when a marshmallow is heated, the temperature of gas inside the bubble increases. That's going to increase the pressure, so the volume of the bubble increases or expands until the pressure inside equals the pressure outside. When a marshmallow is placed in a closed filter flask and all the air is sucked out of the flask, the atmospheric pressure drops below the pressure of gas inside the bubble. That causes the air bubble to expand until the pressure inside equals the pressure outside. Let's take a look at these two situations. Stop the video and answer these two questions. And the answers are: as the temperature inside the tire drops, the pressure drops. And the big balloon has more air in it than the small balloon. You have 20 mils of air at 25 degrees Celsius and 1 atmosphere pressure. So air doesn't escape, you plug the tip. You compress the gas to 15 mils. Stop the video and figure out the new pressure. And the answer is: as the volume drops, the pressure increases. From the previous examples, we found that pressure is directly proportional to temperature, pressure is inversely proportional to volume, and volume is directly proportional to temperature. We also found that pressure is directly proportional to moles. Combine all those relationships into one equation and we get the ideal gas law. When we're comparing one set of conditions to another, this is the equation we can use. For the syringe situation, here's what we can do. Compressing the air in the syringe from 20 mils to 15 mils increases the pressure from 1 atmosphere to 1.3 atmospheres. And this equation relates the density of a gas to molar mass, pressure, and temperature. This picture explains the breathing process. Stop the video and identify the gas law involved. And the answer is: when you inhale, your diaphragm contracts, your chest expands so that your lung volume increases. The pressure inside your lungs drops below atmospheric pressure. That forces air into your lungs. The reverse is true when you exhale. Have you been in a hot air balloon before? Or maybe you've seen pictures. Stop the video and answer these questions. And the answers are: as temperature increases, the density decreases. And for question D, as the molar mass increases, the density also increases. So light helium floats and heavy argon sinks. Here's a few things you can try with plastic bottles. Stop the video and answer these two questions. And the answers are: the pressure inside the bottle equals the pressure outside the bottle when hot water is poured into the bottle. Cap the bottle. The water starts to cool. As the temperature of the water drops, the temperature of the air in the bottle drops. This causes the pressure to drop below 1 atmosphere. The bottle collapses, that is, the volume decreases until the pressure inside the bottle equals the pressure outside the bottle. Same thing happens in part B.